here. For example, here, for the phosphorus, once it gives the additional electron, the core or the nucleus of the phosphorus will become positively charged. So here, it will become positively charged. So that electron can move around, but in the phosphorus atom, there is a positive charge left behind. So the total material means still charge neutral, because you add additional atom into the material, and that atom itself should be charge neutral. Similarly, for the p-type doping, this boron will be negatively charged. You give additional hole, but this nucleus of the boron will be negatively charged. That's why we have this conclusion: the material is still charge neutral, even under doping. Any questions here? All right. So, what is the reasonable number of the dopants? So let's say, what is the concentration of doping into the silicon? What is the reasonable number? And here we have those two numbers there. We have derived that before. The atomic density is at 5 times 10 to the power 22. And we know that the intrinsic free carrier at room temperature, this number depends on the temperature, is 1.5 10 to the power 10 at room temperature. So as I said, this is too low for conducting current, because 1 out of 10 to the power 13 found broken. So if you want to increase the conductivity of silicon, you have to dope the silicon with those dopants, either donors or acceptors. So what is the reasonable doping density? So here it says typically the doping density is in the range of this one, 10 to the power 15 to 5 times 10 to the power 18. This is the typical doping density, that ND or that NA, depending on the type of doping. And as you can see here, this number is much higher than the intrinsic free carrier without doping. So we discussed before, if you dope, then the electron density will be determined by this doping. Or let's say P equals to NA. Because the number you see there, 10 to the power 15, is much larger than the intrinsic free carrier density. Orders of magnitude higher. So if you do 10 to the power 15, like donors, then your electron density will be 10 to the power 15. You can ignore that intrinsic part, because that is way low than the doping density. So what is the high end for the doping? So here is that the highest is about 0.1% of the atomic density of silicon. That is roughly, because this is atomic density, if it's 0.1% of that, it will be like 5 times 10 to the power 19 per centimeter cubic here. So this is the high end, because still you want to maintain this majority of this material as silicon. Then it can maintain the silicon crystal structure. And if you have too many other materials, then it becomes another material. It's no longer an impurity. So here to the high end, if you still want to maintain the silicon structure, then you can replace at most like 0.1% of the silicon. That will translate to that doping density, 5 times 10 to the power 19. Of course, here you have a law to tune the doping density. Therefore, you can tune the conductivity of your silicon. Right? The higher the doping, of course, more electron or more holes, then more conductive. So that's why we like silicon, because you have some mechanism to change the conductivity, and then you can make your device out of those properties, give you your desired current level. So any questions here? All right. So this is for this bound model. Since we still have time, so let's move on to the next lecture. Sure, can you end this and start